To talk about exception handling a little bit. Obviously, exception handling is a big part of C++, and exception safety is one of the key issues there. We talked a little bit earlier about, state consistency of objects, and exception safety is a really important part of that. So C++ exceptions are generally pretty easy to generate. They're usually used to basically signal as out-of-band error codes, allocation errors, sometimes used for parsing errors, erroneous input, stuff like that. So they're expected to happen from time to time, and in general, the code paths that do exception catching are generally okay, although not always. The most interesting exception that you would be considering when auditing applications is most probably the memory allocation, because they happen so frequently that they're pretty easy to forget about. For example, you can have an expression that just adds two objects together or something, and it's easy to forget that actually is probably going to call an overloaded operator plus, and that could do some sort of memory allocation, throw an exception. So they can happen a lot, and they're pretty easy to forget about. Now, although they're used to return errors generally, they're not the same. As we said before, they're harder to ignore. The developers need to specifically decide to handle it and then ignore it. And if they don't, it generally results in a controlled program crash, more or less. The point is, though, that they're not always particularly harmless, because you have to consider what happens after the exception is thrown. And that's where we talk about exception safety. So for a function to be exception safe, basically the invariants, the member variables of an object must maintain some sort of consistency so that they can be that object can be operated on okay afterwards, or it can be destroyed if it's an automatic object and it's going to be destructed automatically. We've got an example of how you could get that wrong. You can see we've got like this module class here, and it requires some sort of authentication. And you see the authenticate function takes like an auth type and some sort of authentication blob. And they've got to point it to a credentials object, and basically if that's non-null they delete it, and then they allocate a new one. So obviously the problem there is the new credentials line there. There's a good chance that that'll do some sort of allocation and will throw an exception as a result if it fails. The problem here is that essentially the module object that executes this code has a chance to be inconsistent at this point, because it's still got it's basically got a stale pointer in M credentials. So if the new credentials thing throws an exception, then this object can no longer be operated on. It's especially dangerous if this object is on the stack, because the exception might trigger a automatic object destruction when you do a stack unwind. And you can see that the destructor there checks if M credentials isn't null, and if it isn't, it's going to delete it, and it's going to lead to a double delete scenario like we talked about earlier. We're going to digress a little bit here to talk about Windows exception handling, because it ties into C++ exception handling in Microsoft world, and so we're going to have to talk about that a little bit. So, as everyone probably already knows, Windows has SEH, which is basically a native exception handling framework provided by the operating system that allows exceptions to be caught, handled, and examined and handled on a per-thread basis. This functionality is basically used to implement the non-standard try, except, and finally keywords that you can use in C or C++ with Microsoft compilers. We don't really have time to go into the internal structures of how SEH works, so we'll just point you to some really good resources on that have been done before us. There's the excellent article by Matt Petrick on the subject, and there's also a really good article by Igor SK that talks about exception handling, and also a number of other interesting things related to the Microsoft Visual C++ compiler. But anyway, basically C++ uses this exception handling framework and has a specialized exception code to recognize that a C++ exception has been thrown. And what happens is a call to CXX frame handler provided by the CRT library is basically inserted by the compiler as an SEH handler. And for any functions that need to catch C++ exceptions, destroy local objects, and do that sort of thing. Now, the CXX frame handler function actually maps out what code should run as a result of a particular exception being thrown, and the handler code will be invoked accordingly, which might be, exception handling code or, again, local object destruction. The way it does this, again, it's more than we can go into here, but essentially a structure is passed to CXX frame handler, which, among other things, contains a pointer to a structure that basically maps handler code with what it needs to run on receipt of various exceptions. So anyway, basically, the important thing here is that because C++ is laid on top of the SEH exception handling, C++ applications can possibly respond to native system exceptions. Basically, system exceptions can be caught by catch-all blocks within C++ code using the catch ... and also localized object destruction can happen as a result of system exceptions. Now, this isn't always the case. It depends on exactly what compiler you use and the compilation environment you use. So basically, Visual Studio 2005 gives you the choice of whether you want this behavior or not by one of two compiler flags. The first is EHSC, which is synchronous exceptions, and it essentially means don't catch system exceptions, don't do object destruction when system exceptions occur, and so on. And this is the default behavior in Visual Studio 2005. Alternatively, developers can, can pass the EHA flag to the compiler, which is asynchronous exceptions, which means that, the C++ catch blocks can catch system exceptions, and local object unwinds can happen as a result of system exceptions. The previous compilers before 2005 always default to this second behavior. They always did asynchronous exception handling, and in fact, you didn't have a choice. What's interesting about that is C++ exception safety, in the context we talked about it before, can essentially be violated because system exceptions, as implied by the asynchronous nature of them, can happen at any point in time, and it's kind of counterintuitive to even an experienced C++ developer, because they can develop code that's, exception safe as far as C++ is concerned, but if random exceptions get thrown from the system, then it's hard to accommodate for that. So basically, if you look at all the different system exceptions that can happen, you see why this hasn't been too much of a problem in the past. Essentially, it's pretty hard to cause some of these exceptions, and if you can cause them, then there's already a problem in the application. But we're going to consider the status Stack Overflow one for a minute here. Really quickly, we're going to talk about how a Stack Overflow exception is thrown. So basically, when a thread allocates a stack, it has a chunk of memory carved out of the virtual address space reserved for it exclusively for use by that thread stack. And that's called the reserved stack memory. It's not actually committed. And the amount of space it reserves actually depends on a value read from the PE header, but it can also be overridden with a parameter to create thread. Then they'll go ahead and actually commit a portion of that so that they can use it for regular stack usage. And again, that's read from the amount they commit is read from the PE header, or can be specified explicitly to create thread. And that'll be capped with a guard page on the end of it. So essentially, a guard page is the same as any other regular page. In this context, it'll be a read-write page, but it'll have an additional property, which is the page guard property that'll be set on that particular page. And then you'll have a stack that's ready for use. Now, what happens is the thread will go ahead and use the stack as usual, and it keeps growing until it touches the guard page. And when the guard page is touched, that page guard property is removed. So the guard page becomes just like a regular stack page, but a status guard page violation exception will be thrown. Now, this is actually pretty transparent to the application, because generally what happens is the kernel will catch it and check, when it gets a guard page violation, it'll check whether it's actually as a result of a stack overflow. And in the case it is, it will basically allocate a new page from the reserve stack memory, providing there's at least 2 spare pages left in the reserve stack memory, and it'll carve one of those out and make that a new guard page. So essentially, it'll allow you to keep growing the stack until there's no room left. That last page, incidentally, of the reserve stack memories will never actually be allocated. It's sometimes called the hard guard page, and it's basically there because essentially when you've used up all the stack and they can't grow anymore, they throw a status stack overflow. And they never want to map that last page in, because if you have an exception handler to handle a status stack overflow explicitly, they don't want you to accidentally, traverse into adjacent memory blocks. Okay, so essentially stack overflow exceptions can conceptually happen at any point in time. If you think about it, they can be generated for any push instruction, any call instruction, or any move instruction that's doing some sort of local variable access. But in reality, they don't often happen because the default reserve size for a stack is around 1 meg, and most threads use nowhere near that. Now, in order to actually trigger this event to happen, usually you'll require some sort of arbitrary stack allocation using alloc, or some sort of recursive function call. Now, it turns out not to be too interesting, because usually the faulting thread will just terminate if you've used all the stack up. But there's cases where it can be interesting, and that's basically when exception handling is in place. Now, essentially, poorly protected code sometimes maybe lazy or just by design does catch-all exception handling and will continue execution. And basically, if we can trigger an exception at a relatively inconvenient time as far as the application is concerned, it might have bought us something. And that something is basically the ability to execute a very rarely traversed code path that would basically never happen in the normal operation of a program. So in the context of C++, local objects can be destroyed at an arbitrary point in time. And if you think about that, that can be very bad, because like I was saying before, we have functions that are conceptually C++ exception safe, but if you have the function in the middle of updating an object and a system exception like a stack overflow is thrown, that object might be inconsistent, and then the local object will be destroyed during a stack unwind. So that would be particularly bad. Of course, after the exception is triggered, you don't actually have much stack space left, because you're on the last stack page available. So your stack space is limited, but it's not particularly restrictive. You have 4K, and that's usually enough to execute at least long enough to do something bad. So we'll have a look at how that could be a problem. This is from the latest Windows SDK. It's in their string class. It's their string deallocator, and it requires a little bit of explanation, so I'm going to try and do this as best I can. Essentially, they've got this union BX, which can either be an 8-byte buffer or a pointer. And the only way they tell the difference between them is a member variable called myres. And if myres is less than 8, then they know that they're just using that character buffer. If it becomes larger than 8, then basically they allocate memory for the string data somewhere else, and they use BX as a pointer to that string data. So you can see that when they're tidying it up here, they basically go, if myres is greater than 8, then they know that they're using a pointer, so they get that pointer out of the union, and they go ahead and copy the first 8 bytes over into the union, into the buffer, and then they deallocate the pointer. So you can imagine that if you'd used up a whole bunch of stack and then called this function, and then the deallocate function was to trigger a stack overflow exception, for example, this would be particularly bad, because they have yet to reset myres to less than 8. So during a stack unwind, the destructor actually calls this tidy function again, and because myres hasn't been reset, they think the union BX still has a pointer in it when you've in fact copied character data over the top of it. And so then you're going to end up with some sort of arbitrary freeze situation. Okay, so basically using stack overflow exceptions,